For the data science assignment 3, we had to answer following questions. First question was elbow in VAE and diffusion models. So the evidence lower bound or elbow is like a spatial scoring system for variational autoencoder. It balances two things: how well we can reconstruct our input data and how organize our latent spaces. So think of it as a coach who is training you both to paint accurate copies of painting while also keeping your studio organized. So both of these goals matters. In diffusion model, we use a similar idea but with the twist. So instead of organizing a Latin space, we are learning how gradually removing the noise from the data, and elbow help us to ensure denoising process works correctly. So while VAE and diffusion model look different, they share this core principle of optimizing a lower bound, and it's just applied to different problems. One clean up the latent space, and the other one will clean up the noisy data. Question 2 was related to the beta VAE. The beta VAE adds the adjustable knob to our VAE framework. So this beta parameter controls how much we care about latent space organization versus the reconstruction quality. So when the beta is equal to 1, we are using the regular VAE with balance approach. When beta is higher than 1, we are prioritizing the cleaning and organizing the latent space even if reconstruction aren't perfect. So this often gives us more interpretable features like one dimension controlling color and another will controlling the shape. When the beta is less than 1, we focus more on making beautiful reconstruction, caring less about the latent space structures. So what is cool is that the higher the beta value tend to give us those nice clean lattice dimension that everyone can understand and work with, making beta VA super important for interpretable AI. Question 3 was related to the diffusion process. So the diffusion models work like this, where we start with the real image and gradually add random noise until it becomes completely static, like the old TV with no signal. Then we train a neural network to do the reverse, to take the noisy image and predict what they look like with the slightly less noise step by step. So when generating new images, we start with the pure random noise and use our network to gradually clean it up until we get the clear realistic images. So it's like if you spill the paint on a photo and then learn how to remove the paint one drop at a time, and eventually revealing the completely new photo that never existed before. So this process has become incredibly popular because it generates amazingly high quality image while being more stable to train than the earlier methods like GAN. Question 4 was about Gaussian VAE loss function. So while training a Gaussian VAE, our loss function has two main parts. So first one is the reconstruction term that simply asks how different is my output from the input. So for images, it's measuring the pixel difference between the original and the reconstructed image. Second, the regularization term that pushes our latent variable to follow a standard normal distribution. So this is what let us sample from the model later. The key insight is here is using that tree parameterization trick. Instead of sampling directly from our encoder's output, we sample from the standard normal distribution and then we shift and scale it. So this clever trick turns the random sampling into the deterministic function with some fixed noise and allowing gradients to flow through the network during the training. And without this trick, VA simply wouldn't work in practice. Then the fifth question was about the research paper overview. So in this course, we have studied many research paper based on the revolutionize AI. So the VA paper introduced the framework for encoding the data into the continuous space, and we can sample from it plus the clever reparameterization trick. Then the diffusion model survey explained these techniques behind the tools like DALI-E and stable diffusion. Then hybrid norm showed how better normalization make transformer models train more stably, crucial for the systems like ChatGPT. Then original GAN paper introduced the genius idea of having two networks which compete against each other. One is creating fake while other is trying to classify them among real and fake. Then DC GAN brought us the convolutional neural network to the GAN, which dramatically improves the image quality, while Laplacian pyramid GAN showed how to generate the images from the course to find details. So each of these papers represent a breakthrough in getting machines to create the realistic content and building upon the previous innovation to create today's impressive generative AI. And the question 6 was about the importance and applications. So all these models, GAN, VAE, diffusion models, transformers, are the basic building blocks of modern AI. So they are behind everything from Instagram filters to advanced chatbot. So each of these models taught me something unique. Like GAN showed me how competition drives improvement. VAE introduced the probabilistic thinking, while diffusion models demonstrated the power of gradual refinement, and the transformer reveal the importance of context. So all these skills have transformed how I approach problems and how can I understand research paper, the design experiment, and implement the complex systems. And looking ahead, I plan to use this knowledge for creative AI tools or in education tech. The most valuable thing I gained wasn't just the technical knowledge, it was about understanding how machine can learn to create, which will remain valuable regardless of how AI evolves and how to get thorough with each of the research paper and everything. Thank you.